Welcome back. In this session, we'll solve some examples of realizing a discrete system. Well, let's start. So, let's take an example. Let's suppose the transfer function of a system is given by h of z, and h of z is 8 z cubed minus 4 z squared plus 11z minus 2 divided by z cubed minus 1.25 z squared plus 0.75 z minus 0.125. So this is our transfer function of the system. Now let me bring this transfer function in the standard form. Standard form, I mean taking z cube common to both, this will be in z inverse form. So if you take z cube common from the numerator, it will be 4 z minus 1, sorry, minus 2 plus 11 z minus 2 minus 2 z minus. Same way we will keep z cube common, so it will be this. We'll have 1 minus 1 minus 2.5 z minus 1 plus 0.75 z minus 2 minus 0.125 z minus 3. Alright, so this is how we. Now you can cancel the z cube and z cube. We are left with 4 z inverse plus 11 z minus 2 minus 2 minus 2 1 minus 1.25 z inverse plus 0.75 z. Alright, so this is our transfer function of the system. Alright, now let me illustrate that procedure step by step that we already learned. Right. So first let's do the direct form one structure and direct form second, then direct form second structure. So how do we do the direct form one structure? And what is the procedure followed in direct form one structure? What we do, we write it out like this: h of z, which is the output by input, and we write it like this. We say we first arrange the zeros. We first realize the zeros, then poles. That's the difference between this. That's what we do in direct form one structure. So 1.25 minus inverse plus 0.75 minus z square minus 0.125 z cube. Alright. So what we'll do, we'll arrange it like this. We say y of z by x of z is equal to hz of z and multiplied by hp of z. Now what do we mean by hz of z? Where hz of z is equal to 8 minus 4 z inverse plus 11 minus z2 minus 12 z cube, and similarly hp of z is this 1 by 1 minus 1.25 z inverse plus 0.75 z minus 2 minus 0.125 minus z cube. Alright, so this is how we realize the system. In other words, our goal is to first realize this part, and you can arrange it in the block diagram form like this. So in the block diagram form, we can draw it like this. We say first we have one system, then we have another system, and these are connected. And the input to this system is x of z, output is y of z, and this is our h of z, this is our hp of z. Alright, so this is our hp of z, and let's call the input, the intermediate, as p of z. This is just a minute, right? So first let's realize this part. Let's realize it. So pz is equal to hz x of z, right? Hz of z multiplied by x of z. What's hp of z? Hz of z is this 8 minus 4 z inverse. So let me write it first. So this is 8 minus 4 z inverse plus 11 z minus 2 minus 2 z cube multiplied with x of All right. So taking the multiplication, this will be 8 x of z minus 4 z inverse x of z plus 11 z inverse x of z minus 2 z cube x of z. All right. So taking the inverse z transform here, taking the inverse z transform, p of n will be equal to 8 x of n minus 4. What will be the inverse transform of this? This will be x of n minus 1 plus 11 x of n minus 2 minus 2 x, sorry, small x of n minus. So let's realize this part first. So let's realize this part first. Please learn this. This is very important. Please follow the steps. So first I will get this. So first I have x of n, then I will pass this through a multiplier with a multiplying value 8. So this is x of n. Now I have x of n 8 times x of n, right? Let me use the numerical over this side. Let me write the value later. Alright, then I will get this, right? So then I will get this. First I have to get x of n minus 1. So to get x of n minus 1, I will pass this to a delay. Then this here I have x of n minus 1 available here. Then I will pass this to a multiplier with multiplier value minus 4. Alright, with multiplication by minus 4. Then I will again delete. I will get x of n minus 2. So what I am going to do, I am going to again delete. Then I have x of n minus 2, and then I will pass this to a multiplier with multiplication value 11, right? Then I will again delete to get x of n minus 3. So we'll again delete. This is the notation for delay, and then we'll finally pass this through a multiplication with a multiplying values minus 2. So this is minus 2. Now let me write the values. Now let me write the signal values. Right. So this is 8 x of n. This is minus 4 x of n minus 1. This is 11 x of n minus 2. This is minus 2 x of n minus. Alright, this is our x of n minus 2. Now what we'll do, we'll start adding these. So first let's add these two. So we'll add this and this. You can see we have obtained what we have obtained this part. We have obtained this part. So we added these two. Now then we'll add the sum of these two with this, right? So add this, what is available here, then we'll add it to this. So adding this to this, what we have now realized these three terms, right? Then we'll finally add this to this, and we have realized the whole P of n. So this is our P of n. All right. Now, so this is the first part of that equation. Now the second part is this y of z. So our aim is actually to get y of n, right? So y of z, let me write it here, is hp of z multiplied by p of z, right? So what's hp of z? Some 1 by, I think 1 minus 1.25 z inverse here plus 0.75 minus z was minus 0.125 cube. Yeah, now rearranging the terms here. Rearranging the terms, so this will be y of z will be multiplied by this. Zero point 125, right, is equal to p of z, right? So y of z will be equal to, let me multiply this will be 1.25 z inverse y of z plus 0.75 z inverse z, this was minus 2 y of z minus 0.125 minus 0. Please see whether I'm doing it right or wrong. So this is p of z. Alright, taking the inverse z transform here, what we'll have y of n minus 1.25, the inverse Z transform of this will be y of n minus 1. Inverse Z transform of this will be y of n minus 2. Inverse Z transform of this will be y of n minus 3 is equal to p of n. Now I need y of n, so I will shift every term on the right hand side. So I will y of n is p of n plus 1.25 y of n minus 1 minus 0.75 y of n minus 2 plus 0.25 y of n minus 3. So let's realize now this part. Alright, now let me do it with the same structure that we have already realized, right? So one input is p of n. So one input is p of n. Then I need 1.25 times y of n. Let's suppose the y of n is available here. So this is our y of n. Then what I am going to do? We are going to delay it. So we are going to delay it. Right. So this will give us y of n minus 1. So this will give us 1 of n minus 1. And we'll pass this through a multiplier. And the multiplication value is 1.25, then that will be 1.25 times y of n. Then what we will do, we will add this term and this term. P of n is available here, so we add these two like this, right? Now let me do it at the end. Before we do this, let me do this at the end. That's the procedure that will follow. First, let me get this term. So let us get this term. Again, we'll delay it. So we'll have y of n minus 2. Then we'll pass this through a multiplier whose multiplication value is minus 0 minus some 0.75. Huh? So multiplication value is minus 7.5, 0.75. Then we'll again pass this through the element. So this will be y of n minus 3. Then we'll pass through a multiplication value which has a value equal to 1.25 and like this. Then what we'll do, we'll start adding these. So first let me add these two. So this is available here. Then adding this, what we have minus 0.75 y of n minus 2. Here we have 0.125 y of n minus 3. So I am adding these two, adding a summer. So I am taking the sum of these two terms. Now adding this to the next term means with this term. Here I have 1.25 y of n minus 1. So adding this to this, I have now this part. I have realized this whole part. Next, what I'm going to do, I'm going to add the p of n. So adding the whole term to the p of n, and that is our y. This is how we realize the structure. So this is the direct form first structure. Here we have all zeros. Here we have all whole. This is how we realize in the direct form one structure. Now in the direct form second structure, what we'll do, in the direct form second structure, second structure, let me rewrite the expression again. So our goal is now direct form second of the transfer function or the system. Let's return by this transfer function. So first I have 8 minus 4 zeros. Please check it. Rewrite it right around. This will be 1 minus 1.25 inverse 0.75 minus z 0.125 cube. Alright. Now what we do in the direct form second structure, we first write the poles, then the zeros. We'll arrange it like this. We'll say this is 1.125 zeros plus 0.75 z minus 0.125 z minus 3. Then we'll write the zero term. 8 minus 4 z1 plus 11 minus 2 minus 2 z raised to minus 3. So this is our y z by x statement out for the input. That's referred as h of z, right? So let's call it hp of z, and this is h z of, right? So if we draw it as a block diagram form, we'll write it that we have two blocks that are connected in cascade like this. If you remember the unit 1, we said if two blocks are connected in cascade, their impulse response will be multiplied. So their transfer functions will be multiplied. So this is HP of Z. So this is HP of Z. This is HZ of Z, right? And this is our input, and this is our output, right? And let's call P of Z. Let's call the intermediate signal as P of Z, right? So what will be P of Z? So P of Z will be equal to X of Z multiplied by HP of Z, right? HP of Z. Alright, so substituting the value of HP of Z, what's HP of Z? Please copy the values first. HP of Z will be simply X of Z, it's HP of Z 1 by 1 minus 1.25 Z inverse 0.75 Z raised by minus 2 minus 0.125 Z cubed. I think I'm right. So this is our expression. Now rearranging the terms. So we can write it X of Z is equal to, so we can write X of Z is equal to P of Z after we do the cross multiplication. Z cubed, right? So this will be P of Z minus 1.25 P of Z plus 0.75 Z squared P of Z minus 0.125 Z cubed. Alright, so taking the inverse Z transform here, taking the inverse Z transform, we have X of n is equal to P of n minus 1.25. The inverse Z transform of this will be P of n minus 1 plus 0.75 P of n minus 2 minus 0.125 P of n minus. Alright, now I will write first P of n. On one side I will write P of n and the rest of the terms I will write on the other side. So when I transfer this will be plus P of n 1 plus, sorry, this will be minus now. So this will be minus 0.75 P of n minus 2 plus 0.125 P of n minus 3. Alright, so let's realize this part. Let's realize this equation. So I have input X of n. I'm adding this input to this term, right? P of n. And let's suppose P of n is available here. So this is our P of n, right? And then what we'll do, we'll pass this through a delay element. I will get P of n minus 1. So this will be P of n minus 1, right? Then what we'll do, to get P of n minus 2, we'll again pass it through a delay element. So we'll again pass it through a delay element. So this will be P of n minus 2, right? Then we'll again pass this through a delay element to get P of n minus 3, because the last term that we need is P of n minus 3. So we'll again pass this through a delay element. So this will be P of n minus 3. Alright, then what I'm going to do, I'm going to pass these terms through a multiplier. So the multiplication value is 1.25. Here the multiplication value is minus 0.75. Here the multiplication value is 0.125. Alright, so what I have here, here and here, I have these signals. So what I have here is 0.125 of n minus 3 Here I have 0 minus 0.75 p of n minus 2. What I will do, I will first add these two. So I'll use a summer here and add this with this. Now I have realized this. Then I will pass, I will add this term to this will give us this term. Then finally I will pass this term to this will give us P of n. So this is how we realize the first part of this equation. Now the second part means when where y of z is equal to P of z times x of z. What's P of z? P of z is the intermediate input. Sorry, I had it in the wrong. It's not x of z. LZ of z. Z substituting the value of LZ of z is 8 minus 4z inverse plus 11z minus 2 minus 2z, right? So rearranging the terms, it will be 8 of z minus 4z inverse p of z plus 11z in z raised to minus 2 p of z minus 2z cubed p of z, right? So this is our y of z, this is the output. Alright, now taking the inverse z transform here, we get y of n is equal to 8 p of n minus 4 p of n minus 1 plus 11 p of n minus 2 minus 2 p of n minus 3, right? So now have a look at this. We need p of n, we need p of n minus 1, we need p of n minus 2, we need p of n minus 3. All right, now p of n minus 1 is available here, so we'll pass it through as multiplier, so minus 4. Then we'll pass this through multiplier here, p of n minus 2, that's 11. Then we'll finally pass this through a multiplier, minus 2. And what I have, and this p of n I will pass through 8, like this. So let me write the signal values first. So this is minus 2 p of n minus 3. This is 11 p of n minus 2. So first let me add these two. So this I will add to this. Then here I have minus 4 p of n minus 1. Then I will add these two terms with this term. This will give me this whole term. This will give me this whole term. Then I will add finally this to that. 8 p of n, and this is our value. This is how we realize it. And on this side, remember on this side we have poles of the system, on this we have zeros of the system, and this is referred as direct form second structure. See, there are only half of the delay elements over here that we require in direct form. Direct form 1. Have a look. Here in direct form 1, we have how many delay elements? 1, 2, 3, 4, 5, 6. And in this direct form 1, we have how many delay elements? 1, 2, 3. So half of the memory is required in direct form second. This is the advantage of direct form second. So in direct form second, there is an advantage of memory blocks are saved here, right? Now there are other ways to realize this. One is the cascade realization. Another realization is parallel realization, and another is lattice realization. That's very popular these days. Right? I will not show these examples. Please do it yourself. All right, please do it yourself. One more very important point that I want to make. See, if you see the general Anathola difference equation, it is mostly in this form. Plus summation k running from 1 to n, a k y of n minus k is equal to summation k running from 0 to m bk x of n minus k. Now, if this is not equal to 1, remember, if this is not equal to 1, if this quotient is not equal to 1, please divide throughout this equation by a naught so that you get a n is equal, y of n, sorry, y of n is equal to 1. If this is not equal, remember, this is, you have to do it. If this is not equal to n, ak a naught y of n minus k is equal to 0, bk divided by a naught. Then try to realize that these difference equations are the discrete time systems. First, bring it in this form. Only then it will be possible to do it in the direct form 1 and direct form 2 structure. All right. Now, in the next session, what we will do, we'll realize the system that has this part equal to 0, that has this part equal to 0. All right. Let's do that in the next session. All right.